Okay, welcome to class. Today we're going to have a look at the third lesson in chapter 5. We're going to have a look at two topics: head-on elastic collisions and collisions in two-dimensional space. Glancing collisions. Okay, first, let's have a look at the head-on elastic collisions. In previous section, we have read about systems involve elastic and inelastic collisions. We applied the law of conservation of momentum and the law of conservation of kinetic energy to solve problems. We also learned about the ideal cases of the perfectly elastic and perfectly inelastic collisions, and learned that in both cases, momentum is conserved. We also discovered that kinetic energy is conserved in the case of perfectly elastic collisions, but not inelastic collisions. In the first half of today's lesson, we will examine in greater details involving perfectly elastic collisions in one dimension. We will calculate final velocities of two objects after elastic collisions in one dimension with equations for special cases. Once again, we consider near perfectly elastic collisions in one dimension, which is shown here in figure 1. Okay, first of all, let's consider the perfectly elastic head-on collisions in one dimension. In a one-dimension head-on elastic collision, two objects approach each other from opposite directions and collide, right? In such collisions, both momentum and the kinetic energy are conserved. We can derive expressions for the final velocities of two objects in a head-on collision in terms of the initial velocities and the object's masses. So suppose an object of mass m1 travels with initial velocity vi1 and collides head-on with an object of mass m2, traveling at velocity vi2. If we assume a one-dimensional collision, we can omit the vector notation for velocities and instead use positive and negative values to identify motion in one direction or the opposite direction, right? We began the analysis with the conservation of momentum. The conservation of momentum tells us that the total momentum of the system in the initial state, which is m1 vi1 plus m2 vi2, should equal the total momentum of the system in the final state, which is m1 vf1 plus m2 vf2, which is here. The first equation, it's the very first equation here. Okay, let's call this equation number 1. And we can rewrite equation number 1 by bringing all the terms with m1 to one side and all the terms with m2 to the other side, right? And common factoring the m coefficients, which get us the equation number 2 here. Since this is an elastic collision, we also have conservation of total kinetic energy, which gives us 1/2 times m1 vi1 square plus 1/2 times m2 vi2 square equals 1/2 times m1 vf1 square plus 1/2 m2 vf2 square, which is here. And then we can simplify this equation to a form like this. And we call this equation equation number 3. And also we can divide equation number 3 by equation number 2. And this gives us equation number 4 like this. Okay. And rearranging equation number 4 to isolate VF2 on the left gives us VF2 equals VI1 plus VF1 minus VI2. Let's call this equation number 5. Then substitute equation number 5 into equation number 1 to express VF1 in terms of the masses and their initial speeds. This gives us these steps here. And we can collect the VF1 terms on the right side of the equation and terms involving initial velocities on the left side. Then collect like terms and divide out common m coefficients. So finally, we have this relationship here. Difference of m1 minus m2 times vi1 plus 2m2 vi2 equals the sum of m1 and m2 times vf1. Then divide both sides by the sum of m1 and m2 to isolate vf1. This gives us a formula like this. The final velocity of m1, which is denoted by vf1, equals m1 minus m2 over m1 plus m2 times the initial speed, the initial velocity of mass m1, denoted by vi1, plus 2m2 over m1 plus m2 times the initial speed of the mass m2, which is denoted by vi2. So this equation expresses the final velocity of the first object in terms of the masses and the initial velocities of the two objects. Similarly, we can rearrange equation 4 to isolate VF1 on the left side and to derive a similar equation for VF2, which is here. Well, this is very similar to VF1, except that on the right side, VI1 becomes VI2 and VI2 becomes VI1. This equation expresses the final velocity of the second object in terms of the masses and initial velocities of the two objects. Well, it is important to note that these equations hold true only for perfectly elastic collisions in one dimension. Okay, in some cases, one of the objects is initially at rest. For instance, if V2 is initially 0, okay, if V2 is initially 0, then you can cancel this term, right? Because Vi2 is 0. And also for VF2, you can cancel this term. Okay, so these are just special cases. But for more general cases, these are the two formulas to calculate the velocity of object 1 and 2 in the final state, given their masses and their initial velocities. Okay, I'll give you 5 minutes to have a look at the formula here. And after that, we'll apply these formulas to solve some sample problems, okay? Okay, let's consider this some problem here, which is about head-on elastic collision with one object at rest in one dimension. So consider a elastic head-on collision between two balls of different masses. As shown here in figure 2, the mass of the ball 1 is 1.2 kilograms, and its velocity is 7.2 meters per second due west. The mass of ball 2 is 3.6 kilograms, and ball 2 is initially at rest. Can you determine the final velocity of each ball after the collision? Okay, I'll give you 5 minutes to consider the problem by yourself, and then we'll have a look at the solution together. You can start now. All right, have we finished? Okay, let's have a look at the solution together. So in this sample question, we have the masses of the two objects and the initial velocity of these two objects. VI1 is 7.2 meters per second due west, and VI2 is 0 meters per second, right? And we want to find the final velocity of the object 1 and 2. Since one of the objects is initially at rest in the head-on elastic collision, we can use the simplified equations. The final velocity for object 1, Vf1, equals m1 minus m2 over m1 plus m2 times Vi1. And the final velocity of object 2, Vf2, equals 2m1 over m1 plus m2 times Vi1. So we can let the negative x direction represent west. For ball 1, we have Vf1 equals m1 minus m2 over m1 plus m2 times Vi1. And then we can just plug these numbers in. This gives us about 3.6 meters per second. And the positive sign indicates that the direction of the velocity is to the east. So for ball 2, we have Vf2 equals 2m1 over m1 plus m2 times Vi1, right? Again, put all the numbers in. The result is negative 3.6 meters per second. So the negative symbol indicates that the direction of Vf2 is to the west. Then we can make the final statement. The final velocity of ball 1 is 3.6 meters per second. Direction is east. And the final velocity of ball 2 is 3.6 meters per second. And the direction is to the west. All right. Do you have any questions? No? Okay, then let's consider another question here. In a bumper car ride, bumper car 1 has a total mass of 350 kilograms and is initially moving at 4.0 meters per second. Direction is east. In a head-on completely elastic collision, bumper car 1 hits bumper car 2. The total mass of bumper car 2 is 250 kilograms, and it is moving at 2.0 meters per second to the west. Can you calculate the final velocity of each bumper car immediately after the collision? Okay, again, I'll give you 5 minutes to consider this problem by yourself. Then we'll have a look at the solution together. Again, you could use the equation we have just learned here at the bottom left. Okay. All right, any ideas? Okay, so basically the method is the same as previous question, right? Except that the initial velocity of the second ball or second car is not 0 in this case. So we can again let east be positive direction and the west be negative. Then the mass of the first car M1 equals 350 kilograms. The initial velocity of the car is 4.0 meters per second. And the mass of the second car is 250 kilograms. And velocity of the second car is negative 2.0 meters per second, right? And according to the formula to calculate the final velocity of car 1 and car 2, we have first VF1 equals M1 minus M2 over M1 plus M2 times VI1, then plus twice of M2 over M1 plus M2 times VI2. Then we can just plug these numbers in. Final result for final velocity for car 1 is negative 1.0 meters per second. The negative symbol here indicates the direction is to the west. And again, we can do the same thing for the final velocity for car 2. And that's 5.0 meters per second. The positive symbol in front of this number indicates that the direction of the velocity of car 2 is to the east. So the final velocity of bumper car 1 is 1.0 meters per second to the west. And the final velocity of bumper car 2 is 5.0 meters per second to the east. Okay, any questions? No? Okay, then let's consider these Hooke's equations on the bottom left here. Next, let's consider two special cases. Using these equations for head-on elastic collisions in one dimension, special cases of collisions such as objects of equal mass produce some interesting results. Okay, so from these formulas, we can have a look at the first type of special case. The first case we consider is that when objects that are colliding have the same mass. That will cancel the first term here, right? And simplify the second one. Okay, so let's have a look at what the formulas become. If the masses of the two objects are equal, M1 equals M2 equals M, okay? For the final velocity for object 1, we have VF1 equals M minus M over M plus M, because they have the same masses now, times VI1 plus 2M over M plus M times VI2, right? And simplify this gives us VF1 equals VI2. Also, we can do the same thing for the final velocity for object 2, which gives us VF2 equals VI1. In other words, when two objects with the same mass undergo a head-on collision, head-on elastic collision in one dimension, you can treat that they simply exchange velocities, almost as if they pass through each other. You understand? Okay, then based on these two formulas, a second special case is that a lighter object colliding with a much heavier stationary objects, which means M1 is much smaller than M2, and VI2 is 0. Okay, so if VI2 is 0, we cancel this term here. Also cancel this term here. So the final velocity for object 1, VF1 equals M1 minus M2 over M1 plus M2 times VI1. Because M1 is much smaller than M2, this is approximately simplify to 0 minus m2 over 0 plus m2, which gives us VF1 is approximately negative VI1. And on the other hand, VF2 equals 2m1 over m1 plus m2 times VI1. Again, since m1 is much smaller than m2, so we can simplify this approximately to 2 times 0 over 0 plus m2 times VI1, which is approximately 0. So in this case, in other words, if an object collides with a stationary, much heavier object, the velocity of the light object is reserved, and the heavier object stays at rest. To put this scenario into perspective, you can consider a collision between a table tennis ball and a stationary transport truck. The transport truck will not move, and the table tennis ball will bounce back with the same speed. Okay, we will explore more special cases in the questions at the end of section 5.4. All right, next, let's consider a new topic, which is conservation of mechanical energy in the first half of this lesson. We have discovered what happens to momentum in head-on elastic collisions, right? So what do you suppose happens to the conservation of the total mechanical energy during elastic collisions? One of the two gliders here, shown in figure 3, has been fitted with a spring bumper. When the two gliders collide head-on in an elastic collision, the bounce is not immediate. If you view the collision in slow motion, you would see the bumper compress initially and then spring back to its original shape. During the compression, some of the kinetic energy of the moving gliders is converted into elastic potential energy. This potential energy is converted back into kinetic energy during the rebound. So if the compression of the spring bumper during the collision is X, then the law of conservation of energy states that the total energy in the initial state should equal the total energy in the final state, right? When the spring is compressed. So we have the following relationship here. In the initial state, the total energy is just the sum of the kinetic energies of the two objects, which is 1/2 times m1 vi1 square plus 1/2 times m2 vi2 square. And equal the right side, which is 1/2 times m1 vf1 square plus 1/2 m2 vf2 square plus 1/2 kx squared. So this equation and the graph in this figure 4, both show that as the spring compresses, the elastic energy increases and the total kinetic energy of the two carts decreases. The total mechanical energy, however, stays constant. As the compression decreases, the elastic energy decreases and the total kinetic energy increases. The total mechanical energy still remains constant. So to determine the maximum compression of the spring during the collision, we can use the fact that when the two gliders collide, they have the same velocity at that point. If they did not have the same velocity at the maximum compression, then one would be catching up to the other or pull away from the other, right? Therefore, at maximum compression, which is closest approach, the two objects must have the same velocity, which is denoted by VF, either for object 1 or object 2. Then the equation above can be reduced to the following here. Well, the total energy in the initial state is 1/2 times m1 times vi1 square plus 1/2 times m2 times vi2 square. And the total energy in final state would be 1/2 times m1 plus m2 times vf square plus 1/2 times kx square. Any questions? Okay, next, let's consider some sample problems in which we'll apply the conservation of mechanical energy to problems involving the physics of spring cards. Okay, first, let's consider this sample problem here. Two-card spring system. Dynamics card 1 has a mass of 1.8 kilograms and is moving with velocity of 4.0 meters per second to the right along a frictionless track. Dynamics card 2 has a mass of 2.2 kilograms and is moving at 6.0 meters per second to the left. The cars collide in a head-on elastic collision cushioned by a spring with spring constant K equals 8.0 times 10 raised to the power of 4 newtons per meter, which is shown here in figure 5. Question A, determine the compression of the spring in centimeters during the collision when car 2 is moving at 4.0 meters per second to the left. Then calculate the maximum compression of the spring in centimeters. Okay, this time I'll give you 10 minutes to have a look at this problem by yourself. Then we'll have a look at the solution together, okay? You can start now. All right, have you finished? Okay, let's consider the solution together. In question A, you can use the conservation of momentum to determine the velocity of car 1 during the collision, right? When car 2 is moving at 4.0 meters per second to the left, then apply the conservation of mechanical energy to determine the compression of the spring at this particular moment during the collision. Consider right to be positive direction and left to be negative, and omit the vector notation. You can simply use the signs, negative or positive, to indicate the direction, right? Okay, first begin with the conservation of momentum equation. We have the initial total momentum equal the total momentum in the final state. So M1 VI1 plus M2 VI2 equals M1 VF1 plus M2 VF2. Then rearrange this equation to express the final velocity of cart 1 in terms of the other given values. So we have VF1 equals M1 VI1 plus M2 VI2 minus M2 VF2 over M1, which is shown here. Then substitute the given values and solve. Simply put all the values in. We have VF1 equals 1.56 meters per second here. So cart 1 is moving at 1.6 meters per second. Direction is to the right because the positive sign indicates the direction, right? The right is our positive direction in this case. So cart 1 is moving at 1.6 meters per second to the right, when cart 2 is moving 4.0 meters per second to the left. Now use the conservation of mechanical energy to determine the compression of the spring, which is denoted by X. We have this equation here, which means the total mechanical energy in the initial state should equal the total mechanical energy in the final state. So in the initial state, there are only kinetic energies from the two objects. In the final state, we have the kinetic energies of the two objects plus the elastic potential energy from the spring. Then multiply both sides of the equation by 2 to clear the fractions, and then isolate the term containing x on one side of the equation. And then divide both sides by k, and then take the square root of both sides. Then we have the formula to calculate the compression of the spring X. So X simply equals the square root of M1 VI1 square plus M2 VI2 square minus M1 VF1 square minus M2 VF2 square over K. We have all the values for the left side, right? So simply put all the values in. We have X equals 2.9 times 10 raised to the power of -2 meters, which means 2.9 centimeters. So the compression of the spring is 2.9 centimeters during the collision, when cart 2 is moving 4.0 meters per second to the left. So that completes question A. You have any questions? Okay, have a look at the solution here. Any questions? All right, if no questions, let's consider question B. So the method is similar, except that in this case, when the spring is compressed in maximum, the velocity of the two cars should be the same, right? So at the beginning of the collision, as the cars come together and the spring is being compressed, car 1 is moving faster than car 2. Toward the end of the collision, as the cars separate and the spring is being released, car 2 will be moving faster than car 1, right? At the point of maximum compression of the spring, the two cars will have the same velocity, Vf. Use the conservation of momentum equation to determine this velocity, then apply the conservation of mechanical energy to calculate the maximum compression of the spring. Okay, first of all, we have mvi1 plus m2vi2 equals m1vf plus m2vf, right? Then factor out the common factor vf. We can have m1vi1 plus m2vf2 equals m1 plus m2vf. Then divide both sides by m1 plus m2 to isolate vf. We have vf equals m1 vi1 plus m2 vi2 over m1 plus m2 here. Then substitute the given values to calculate velocity of both cars at maximum compression. We have vf equals -1.5 meters per second. The negative symbol indicates that the direction of vf is to the left. Now use the law of conservation of mechanical energy to determine the maximum compression of the spring. Clear the fractions first, and then isolate x. So similar to question A, we have the compression x equals the square root of m1 vi1 square plus m2 vi2 square minus the sum of m1 and m2 times vf square over k. Again, we have all the values on the right side. So put all the values in, you can find x is actually 3.5 times 10 raised to the power of -2 meters, which means 3.5 centimeters. So we can make the final statement like this. The maximum compression of the spring is 3.5 centimeters. Okay. Do you have any questions? All right, if you don't have any questions, you can take a 10 minutes break. And after that, we'll dive into the second half of today's lesson, which is about solutions in 2 dimensions. Okay. All right, welcome back. So next, let's have a look at the collisions in 2 dimensions. Glancing collisions. So far, we have learned about collisions in 1 dimension, right? So in the second half of this lesson, we'll examine collisions in 2 dimensions. So as shown here in figure 1, the player is lining up the shot so that the cue ball or the white ball will hit another billiard ball at an angle, directing it towards the corner pocket. So what component of the cue ball's momentum will be transferred to the target ball if the shot is successful? The laws of conservation of momentum and conservation of kinetic energy will apply just as they did for 1-dimensional interactions. However, to calculate momentum for 2-dimensional problems, consider the x components and y components of the force and motion independently. Okay, let's have a look at the components of momentum. Dealing with collisions in 2 dimensions involves the same basic ideas as dealing with collisions in 1 dimension. Now, however, the final velocity of each object involves 2 unknowns. The 2 components of the velocity vector. For objects in motion in 2 dimensions, the change in momentum for each component can be considered independently, which means in x direction, we have the sum of the impulse or sum of fx times delta t equals the change of the momentum, delta px. And same principles also apply in the y direction, which gives us these 2 equations. Similarly, the conservation of momentum equation can also be expressed in terms of horizontal and vertical components. For example, along the x-axis, we have pi 1x plus pi 2x equals pf 1x plus pf 2x. And same principle also apply in the y directions. Therefore, we have another set of equations like this. Consider the collision of 2 billiard balls shown here in figure 2. In this shot, the cue ball labeled with 1 will collide with the target ball labeled with 2, initially at rest, sending it at an angle phi towards the corner pocket. And the cue ball will continue traveling at an angle theta from its original direction of travel. Both objects are traveling at an angle to the directions of their original course. This type of collision is called a glancing collision. So a glancing collision is just a collision in which the first object, after an impact with the second object, travels at an angle to the direction it was originally traveling. Okay, next, let's consider a tutorial in which we'll use components to analyze the physics of a glancing collision. Okay, so let's have a look at tutorial 1, analysis of glancing collisions. In these sample problems in tutorial 1, we'll apply conservation of momentum in 2 dimensions. Okay, so first let's have a look at the first problem. In the game of curling, a collision occurs between 2 stones of equal mass. The object stone is initially at rest. After the collision, the stone that is thrown has a speed of 0.56 meters per second in some directions, represented by theta, as shown here in figure 3. The object stone acquires a velocity of Vf2, which is 0.42 meters per second, at an angle of phi equals 30 degrees from the original direction of motion of the thrown stone. Also, this is shown here in figure 3. Can you determine the initial velocity of the thrown stone? Note here, initial velocity should include both the magnitude and direction. Okay, I'll give you 5 minutes to consider this two-dimensional case. Remember, you can use the theory you have just learned independently in the X and Y directions, okay? All right, have you finished? Okay, let's have a look at the solution together. Okay, so in a collision, the two-dimensional space, note that you can apply the conservation of momentum separately in the two directions. So choose a coordinate system to identify directions. We can let the positive x be to the right and negative x be to the left. Let positive y be up and negative y be down. And then apply conservation of momentum independently in the x direction and y direction. Begin by applying conservation of momentum in the y direction to determine the direction of the final velocity of the thrown stone. Then apply conservation of momentum in the x direction to calculate the initial velocity of the thrown stone. So first, in the y direction, the total momentum before and after the collision are both zero, right? Which means we have P-T-I-Y equals P-T-F-Y equals zero. Therefore, after the collision, we have MVF1y plus MVF2y equals zero. Then divide both sides by m and substitute the vertical component of each velocity vector. Note that the vertical component of the first stone's velocity is directed up, so its value is positive, whereas the vertical component of the second stone's velocity is directed down, so its value is negative. Then we have m times f1y plus vf2y over m equals 0 over m. Simplify this gives us vf1 sine theta minus vf2 sine phi equals 0. So we can rearrange this equation to isolate sine theta. Then we have following relationship here. Sine theta equals vf2 sine phi over vf1. Then substitute the given values and solve for sine theta. We have sine theta equals 0.375. Then apply the inverse sine both sides to solve for theta. And we can get theta is approximately 22 degrees here. So the first stone is traveling at an angle of 22 degrees above the horizontal after the collision. Now we can use conservation of momentum in the x direction to solve for the initial speed of the thrown stone. We have the following relationship. Ptix equals Ptfx. Note that the object stone is at rest before the collision, so its initial momentum should be 0, right? Therefore, we have this relationship here, mvi1x plus mvi2x equals mvf1x plus mvf2x. Divide both sides of the equation by m. We have vi1x equals vf1x plus vf2x. Here. Then we can substitute the known values for the final horizontal velocity components of the stone. Note that all vectors are directed to the right, so all velocities are positive. Then we have vi1x equals vf1 times cosine theta plus vf2 times cosine phi. And then put all the values in. We have vi1x equals 0.88 meters per second. So that's the initial velocity of the thrown stone. Also note that this value is positive. That indicates the direction of the initial velocity of the thrown stone is to the right. Okay, do you have any questions? Okay, if no questions, let's consider another sample problem here, which is about inelastic lensing collisions. So in this problem, we have two cross-country skiers. who are skiing to a crossing of horizontal trails in the woods, which is shown here in figure 4. Skier number 1 is traveling east and has a mass of 84 kilograms, while skier number 2 is traveling north and has a mass of 72 kilograms. Both skiers are traveling with an initial speed of 5.1 meters per second. One of the skiers forgets to look, resulting in a right angle collision with the skis, locked together after the collision. Calculate the final velocity of the two skiers. Okay, again, I'll give you 5 minutes to consider this question by yourself, then we'll have a look at the solution together, okay? Again, remember, you can use the theory in two-dimensional space independently in the X and Y directions. All right, let's have a look at the solution together. Okay, according to the law of conservation of momentum, we have PTI equals PTF, right? Since the initial velocities are at right angles to each other, which is shown here in figure 5, we can calculate the total velocity and momentum using the Pythagorean theorem and trigonometry. So first, we have this relationship here, P squared equals P1 squared plus P2 squared, and tangent theta equals the ratio between P1 over P2. As shown here. So the first gear's momentum is given by P1 is M1 V1, which is 84 kilograms times 5.1 meters per second. Direction is east. So that's 428 kilograms meters per second. Direction is east. The second gear's momentum is P2 equals M2 V2, which is 367 kilogram meter per second. Direction is to the north. The magnitude of the total momentum can be calculated by applying the Pythagorean theorem. P squared equals P1 squared plus P2 squared. This is 564 kilogram meter per second. So here we are just using the vector addition, right? The direction can be determined by applying the target ratio. Target theta equals P1 over P2. And then theta is just arctangent P1 over P2. And this gives us theta equals 49 degrees. So the direction of the two skiers is east of north, 49 degrees. Conservation of momentum tells us that final total momentum of the skiers must equal this initial momentum. Since the collision is perfectly inelastic, both skiers have the same final velocity. Then the total momentum in the final state, PF, should equal M1 VF1 plus M2 VF2, which is M1 plus M2 times VF. Then VF is given by PF over M1 plus M2, which is 564 over 84 plus 72. And the direction is 49 degrees east of north, which is 3.6 meters per second with direction 49 degrees east of north. Then the final statement is, after the collision, the skiers are traveling together with a velocity of 3.6 meters per second, 49 degrees east of north. Okay, so this is just one type of method we can apply. We have used the vector addition directly, right? Of course, you can resolve each vector in the x direction and then the y direction, and add them independently in both directions to solve this problem. Okay, you can choose either one you like. Okay, do you have any questions? Okay, if you don't have any questions, that's the end of today's class. Remember to complete your homework and submit them before the deadline, okay?